Okay, we've reached the highlight of this conference with a guest of honor, Abraham Neyman. And it's not that he's just a guest of honor. I think as we listen to these lectures, I think we should elect him the king of mathematical game theory. Okay. So it's a pleasure to introduce Abraham Neyman to speak about stochastic games, past, present, and future, a personal perspective.
Thank you. So, thank you all for coming. And we had here already several lectures on stochastic games. So, I wouldn't assume that everybody knows what a stochastic game, because there are also a few new faces here. But I would skip in my talk some of the past, present results on some of the fields that have been covered here extensively in some of the lectures. And I would focus on few highlights that I think are important in the theory of game theory, not only on the mathematical aspect, but probably more so or also on the economic applications of a stochastic game. So it will be a theoretical work, but viewing issues that arise in my thinking on the economic applications of some of these stochastic games. So let me, just in case we don't get to the very end, let me mention a few highlights of the talk, which I'll try to convey to you during this talk. The first one will be a characterization of the payoff functions that I will be consider in these stochastic games. We had here a few talks in the past where we took an arbitrarily Borel function of the histories of the game. I would not focus on those at all. I would more be concerned with payoffs that are functions of streams of payoffs. And there I'll characterize them by valuations, which will be payoff functions which are normalized, namely a constant stream of payoffs of 1 will be valued as 1, that they will be linear, and they will satisfy the property of the time value of money, namely if we have two streams of payoffs such that the sum for every k of the payoffs in the first stream is at least as big as in the other stream, then the valuation will be at least as big in the first one compared to the second. So within these valuations, I'll also talk about two subclasses, which are the impatient valuations and the patient ones. We will see them later when we come to it. And then given these valuations, I'll just mention for the history few results about existence of equilibria in the different models. And an important point of my thinking here is that taking into account some imprecision of the valuations, because we could build a model and take some valuation, but we should take it with a grain of salt. If this is the exact valuation, we could think of it as an approximation of some valuations, and therefore I would like to push a new concept of discounting robust equilibria, which will be insensitive to such small imprecision. And I would say up front that the ingredient of it is already in the old paper of mine with Mertens from 81, in one instance of this. And then I'll describe classes of stochastic games that have discounting robust equilibria, after we understand what is this concept. And then I hope the time will allow, I want at least to focus on that. I will speak a little about the new topic, a more recently developed, or at least some not introduced, but developed continuous time stochastic game. And the highlight there, that after we understand what are discounting robust equilibria, will be that all finite ones will have discounting robust equilibria, which is a property that in discrete time doesn't hold. And then I would move into raising some issues and problems in the study of continuous time stochastic game with an infinite state space. And I would come to that when we get there, hopefully, because there will be few new phenomena that arise there that a priori, if you just approach it from a mathematical point of view, maybe you would overlook it. But if you think of some applications of the theory of stochastic games, you will see that these aspects are needed to be analyzed. So let me now, just to understand some parts of the talk, because sometimes I'll refer to a class with finite state, finite actions, equilibria, value, and so on. Let us recall that we have various classifications of stochastic games. So some results will apply to discrete time stochastic games, some to continuous time. Often, at the very start of the talk, we'll focus on finite state and action spaces, and for short we'll call it finite. And later we'll speak also on infinite states or action spaces. We have issues of perfect or imperfect monitoring, complete or incomplete information, zero sum or non-zero sum. Sometimes the problems differ in those two fields. And then we would look on various models like the discounted, the classical discounting, the finite horizon or the undiscounted, and more general valuations. But when I say more general valuations, I refer to valuations with the restrictions I mentioned before. And then we'll speak about the solution concept, which will be value, equilibria, correlated equilibria, and the focus will be on this concept of discounting robust equilibrium. So for those of you who are unfamiliar or haven't been in the previous lectures on stochastic games, that were here already plenty of them, I'll quickly recall the model in words, not in symbols. We have seen many of these symbols. So in a discrete time finite stochastic game, the play proceeds in stages. So this is for the discrete time. At each stage, the game is in one or finitely many states, and each player chooses an action simultaneously from a finite set of possible actions. The player's actions and the state, the current action and the current state, jointly determine both a payoff to each of the players and the transition probability to the new state, to the succeeding state. Before making their choices, the players observe the current state. So the first model is where the state is observed. A play of the game results in a streams of payoffs, which I denote by bold G. G1, G2, G1 is the payoff to player 1. It's a payoff vector, G2 in payoff 2. And of course, there are many possible valuations of the streams of stage payoff. The classical one is the R-discounted valuation, where we normalize the stream of payoffs. Each payoff at stage T is computed in its present value, and we finally multiply it by R so that a constant stream of 1 equals to 1. And the first result is Shapley 53 that proved the existence of a stationary equilibrium in the finite zero-sum case, which stationary means that the strategy at each stage of the game, at every time of the game, that each player takes is only a function of the state. And in this model, it is not important, because you have these strategies, it's not important if the player observes or don't observe the actions of the other player. And each time when we have this stationary strategy, it's a point that should be remembered. And therefore, sometimes when we speak about stationary strategy, there is a big advantage. The result is more robust. And then think 64 prove existence of a stationary equilibrium in the finite non-zero sum case. And I should mention that the finiteness assumption of the model is essential. Levy, PhD thesis, 2013. So the R-discounted satisfies the following properties. As I mentioned, the normalization, the valuation R of the constant streams of 1 equals 1. It is linear. It's a linear functional over the bounded streams of payoffs. And the time value of money means that if we have two streams, G and H, such that for every S, the sum of the payoffs in the first stages of the payoffs in G are at least as those as in H, then the valuation of this stream is at least as big as this stream. There is one additional property of this R-discounted valuation, many, but one that I want to call impatience, that if we look on the valuation of the stream that starts for a long period of zeros and thereafter ones, this converges to 0, where this is the payoff, a long stream of zeros, thereafter 1. A function u on the stream, bounded streams of payoffs that satisfies the first precondition, as I said in the first slide, is called the valuation. And a valuation that satisfies also property 4 is called an impatient valuation. Any impatient valuation is essentially a weighted average of the stage payoffs where the weights are non-increasing in time. So the sum is 1, these are non-negative, and they are non-increasing. And a result which is not difficult to prove, I don't know if it's stated in some place formally, that any finite stochastic game has for every profile of impatient valuations a Markovian equilibrium. Now let us look on the other extreme, which is patient valuation. Patient valuation is a valuation V, so a valuation, you remember, satisfies the first three properties we mentioned. And in addition, the value, if I get for some finite number of stages zeros, and thereafter I'm getting 1, I don't care. It's like it's like equal 1, like the constant stream of 1. I don't care about finitely many entries of the payoff. And an important property or a conclusion of these axioms is that any patient valuation satisfies that the patient valuation of a stream is at least the limit inferior of the sequence of the C0 averages and at most the limit superior of the averages of the payoff. It's important to note that there is non-uniqueness and non-constructiveness of patient valuation. Therefore, and in addition, all patient valuations on converging streams, so if the stream is converging, or if the C0 limits converge, then obviously by this condition, all the non-patient valuations will coincide. Because of the first comment of non-uniqueness and non-constructiveness, it is important that when we do optimize with respect to a patient valuation, the limit inferior of an optimizing stream, thank you, the limit inferior of the optimizing stream should be at least the limit superior of any other feasible stream. In particular, in the optimizing stream, the limit need exist. And one could say that V is the value of the zero-sum game with patient valuation if, and then it wouldn't matter which one because of the condition I mentioned here of optimality, if for every positive epsilon there exists a pair of strategy that guarantee the payoff V for player 1 guaranteed that the limit inferior is at least V minus epsilon, and the strategy tau epsilon of player 2 guarantees that for every strategy sigma of player 1, the expectation of the limit superior of the stream of payoffs that result is at most V plus epsilon. In this case, we say that V is a patient valuation is a valuation that satisfies. Okay. Now a few results about the impatient valuations. So historic results are Hoffman and Karp in 66 proved for a specific class of irreducible game. Blackwell and Ferguson proved it for the big match, and Kohlberg proved it for absorbing games. And one should note maybe that in this proofs, basically they didn't prove exactly what I said. because they considered as if the payoff is the lim sup or the lim inf, one of these payoffs. And it's easier to prove for one of these payoffs than to prove that you guarantee the lim inf, and player 2 cannot do anything better even with the lim sup. And the result of Mertens and myself from 81 is that any stochastic game with patient valuation has a value. In the non-zero sum game, if we look on existence of an equilibrium payoff, which is equivalent to claim that for every epsilon there exists an epsilon equilibrium payoff, we have a sample of results by Soran in 86 that states that constructed an analog of the big match, which we call the Paris match, or I think Frank Theismann called it the Paris match, and proved there the existence. Then Theismann and Vries in 89 proved that, proved that any two-person absorbing game has a value, and VA in 2000 proved that all two-person stochastic games have an equilibrium payoff in the non-zero sum case. Solan proved it for all absorbing three-person games. And an open problem is, I think already mentioned, in a different variant, but they are about with Elon, if any finite stochastic game with patient valuations have an equilibrium payoff. I wouldn't repeat, but I promised a prize, a significant prize for a positive answer for it, not for a negative one. And about existence of correlated equilibrium payoff, here we have the result of Solan and VA from 2000 that prove that all finite stochastic games have a correlated equilibrium payoff, an extensive form correlated, but let's not bother with that. Now, as I said before, evaluation is one that satisfies the first three conditions, and the first question is, how do they look like? What is their characterization? We characterize the impatient and the patient one. Any guess? Any valuation is a convex combination of an impatient valuation and a patient one. And the distinction between them according to the valuation of the stream zeros and then 1, that's exactly the limit of those gives the coefficient for the combination between the patient and the impatient. And any two persons, if we look at the previous results with some techniques that I'll mention later, it follows that any two-person stochastic game or three-person irreversible stochastic game, irreversible means that eventually it's being absorbed, could have at most finitely many state changes, as for any pair of valuations, an equilibrium payoff. Equivalently, for every epsilon, it has an epsilon equilibrium payoff. And similarly, any non-zero sum as for any profile of valuations, a correlated equilibrium payoff. So this is n player, the previous one was 2 pairs. Now, let me point the issue that I wanted to raise about discounting robust. So in applications of stochastic game, it is practically impossible to specify exactly the valuation of each player. Therefore, it is desirable to take into account some imprecision in the specification of the valuation. Therefore, for a given profile of valuation, we wish to find an equilibrium or an approximate equilibrium that remains an approximate equilibrium in all the models with nearby profiles of valuations. But what does it mean nearby? In order to define nearby valuations, we have to define a topology on the valuations. Obviously, the weaker the topology that I'll have, and I'll have a result that it's robust with respect to that, means that we have a stronger result. So I want to define a kind of a minimal topology, the topology that is essential for that. And here it is. The set of valuation V, now a point, if you want to define a topology, it's like defining who are the continuous functions there. and I could start the reverse to say which functions I want to be continuous and say what's the minimal topology under which these functions are continuous. So the set evaluation V equipped with the minimal topology such that for every converging stream, so we have convergence, usually in the game they don't have any convergence, but I want that for the converging stream, the function from the valuation V to its value on that stream is continuous, and this one is a topological space. And I know that there are some economists, or at least pretending economists in the audience, and they would say, patient valuation, there is nothing like that. There is always only impatient valuations, and we should be worried only about impatient valuation. And an important point here is that in addition, any valuation with this topology is a limit of impatient valuations. And therefore, this result of robustness that I was looking is relevant even if you are just interested in impatient valuation. Because if you want to say robustness, you want to say that for every converging sequence of impatient valuations, you have some concept that is all for sufficiently large element in the sequence. But the limits are not going to be, this is not a compact space. The limits are going to turn into not necessarily impatient valuation.
Maybe the economists are not interested in the limits.
Even then, yes, if somebody is interested just in the rational numbers, yes, still he will make a better analysis and statement using the real numbers. So here some of these valuations that are not an impatient valuation are basically limits of impatient valuation, and basically you could envision that as as an approximation. I know it's an impatient valuation, but close enough to this limit, and I want something that will be all in all these points. So an important point to mention is that for two distinct non-patient valuation, there is a converging sequence that differentiate the two. But if I look on patient valuation, they coincide on these converging sequences, and therefore basically the space that I defined is not Hausdorff. If you want to think of an Hausdorff, you have to identify some of these valuations.
You mean V of G equals U?
But that's also a correct statement. That's a correct
Yes.
Topology.
Mike went over the slides, he missed this one. So fix a profile of valuations. The payoff vector X is a V equilibrium payoff of the gamma. This is the game with this valuation, so we have a game model and we have the valuation. If for every epsilon there exists a strategy profile and a neighborhood W of this profile of valuation, such that for every profile of valuation inside, this strategy profile will be an epsilon equilibrium with a payoff within epsilon of X. An open problem. Let me be a profile of patient valuations. Does any finite stochastic game have an equilibrium payoff? Okay, it is stronger than the previous open questions that I said. I wouldn't give a higher price for that because of something that we'll see in a moment. But if we look on that, is that if this is a patient valuation, yes, then basically the result of Mertens and myself from 81 basically proved, without defining this concept, proved that any two-person zero-sum finite stochastic game has a equilibrium payoff. In that case, because it's zero-sum, it's a value. You could say that the game is not zero-sum if the two differ from each other, so it will coincide also there as a value. And one should mention that the following assumptions are essential. Perfect monitoring of the actions is already clear from Ferguson, Blackwell and Ferguson, and it was mentioned here in previous previous lectures. Similarly, finitely many actions is important as proved by Vigeral, and is not essential in absorbing games. And observable states which was one of the assumptions, is important as in the as Bruno showed us, and many other things that he showed. And VA basically didn't state it that way, but it is true that this proof, exactly his proof, basically yields that any two-person finite stochastic game has a near equilibrium payoff. An open problem. Now, before it was a profile of okay, so I start with the profile of patient valuation. And this is still open. But if we will know that this is true, then there is a result that if a stochastic game has a near equilibrium payoff, in the sense, if you remember, the near equilibrium payoff was meant that it's robust around knee, we could perturb the, then for every profile of valuations, the game gamma has a near equilibrium payoff. So if you prove it for the patient one, you get it. The result implies for any for any other profile.
A U equilibrium payoff.
A U equilibrium payoff. Thank you.
Again, it's still correct.
Again. It's still correct, but yes. So this should be knee. Yes, thank mu. Thank you. And one other result, which follows from something I said, but maybe you haven't noticed, that something more is true, that for every epsilon larger than 0, there exists a profile, a list of strategy profiles and payoff vectors, such that for every profile of valuation, there is one element of the list that is such that sigma j is an epsilon equilibrium of this game with this valuation with a payoff within epsilon of knee j. And for the few complexity-oriented people that are around, I think that the issue of how big is this set as a function of epsilon is a question that is related to complexity issues. And the question is how big it grows. Yes, if it goes very fast, it will show that the problem of computing the equilibrium is NPR'd. And if it goes very slow, there is a chance to prove that it's not that hard. Now, again, for the economists, I'll skip about it. But you could modify this definition. Here I say it for any, in the definition above of a near equilibrium payoff. Basically, I would be happy if one proved it under the modified definition that knee is an near equilibrium payoff if for every of this game, if for every epsilon there exists a strategy profile in the neighborhood of these such that, and here is the small addition, even if I worry about it just for impatient valuation. Yeah, so give me impatient valuations that are nearby. I want for them to be the solution close to what I want. So I want for the impatient to find a strategy that is an epsilon equilibrium with a payoff within epsilon of x. And the same open problem I mentioned before under the weaker modified definition or the previous one, and the significant price will be awarded for that. Either, yes?
If I have an impatient valuation, can I find a neighborhood of it composed of impatient valuations?
Yes.
So what you said about the necessity of considering patient,
No.
when you should just care?
No. What I say is that I could, if the valuation is not an impatient one, okay? Also, when it's patient, in its neighborhood, there will be also some non-impatient. Okay, always, yes. Okay. How much time I have? Who is the chair?
Oh, you have 20 minutes.
20? Oh.
10?
Oh.
Yeah, that's right.
Okay. So now I'll go fast to give you a flavor. And
Now you have an impatient valuation.
and one of the topics that I'm in love is soccer. And basically thinking about soccer was leading me to think about continuous time stochastic games. I wouldn't tell the story how it brings to continuous time stochastic game, but after thinking of soccer and getting to that, I was wondering how come that economists and us as the game theorists don't consider the continuous time stochastic game. So there are good reasons why not to consider, and there are many more good reasons to consider. So in a continuous time stochastic game, I want to think of the same model as a discrete time stochastic game, but there are infrequent. The decisions are not, you don't have to fix your decision for a period from 0 to 1. You could change it at every instance of time. And therefore, in this game, the play proceeds in time, in positive time t at least 0. And at each time, the game is in one of finitely many states. I am still sticking to the finite state space. And each player chooses an action from a finite set of possible actions. And the player's actions and the state jointly determine the payoff density, because it's an instantaneous payoff, to each player. And now we don't have transition probabilities, we have transition rates. So if before the probability of moving from state 1 to state 2 in a given action was 1/3, I mean that an interval time of dt, the probability will be dt times 1/3. So we have to look on the rates, and this defines a well-defined process, given that we have a profile of strategies of the players. Before making the choices, the players observe the current state. A play of the game results in a string of payoffs. Now it's a continuous payoff. And as in the discrete time, there are many possible valuations. I normalized and linear functions that are defined on the space of streams of bounded streams of payoffs and obey the time value of money property. The analog for the continuous time is clear. No need to define it. And again, if you will think of the discounted formula for a payoff, the analog is clear what it should be. And you could define impatient valuation with the same axioms, the equivalent of the same axioms, and you'll get that, an impatient valuation is of the form, and instead of decreasing weights, you have to integrate with respect to some measure, but the measure has to have the property that it's more mass at the beginning than later, so it's the same as saying that the probability, the mass of the interval t to t plus s is non-increasing in t. And a patient valuation will be again the same axiomatization as before. And again, for the impatient valuation, you will get a property that it's a number in between the limit inferior and the limit superior of the averages. And the same property holds that any impatient valuation is in between. And same result for valuation. A valuation is a convex combination of an impatient and a patient one. And even though you may think of continuous time games as maybe a little more involved than discrete time game, the big surprise was that if you have a profile of valuations and a continuous time stochastic game gamma, so first of all, we could define the same analog of what does it mean to be a near equilibrium payoff of gamma if for every epsilon there exists a strategy profile and a neighborhood W of V such that for every profile of valuations in that, this strategy is an epsilon equilibrium of the corresponding game with these valuations with a payoff within epsilon of this x. And the stochastic game.
Was there an issue of how to define a strategy?
Yes, I'll come to it in a moment. I say there are few issues and more pros, and in a moment after I mention the result, I'll mention the issues. The stochastic game gamma is discounting robust equilibrium if for any profile near of valuation, and if it has for any profile a near equilibrium payoff, the same result with that in this case with the finiteness that I could fill up finite many strategies to fill everything is the same. So this is the result. Any continuous time finite stochastic game has a discounting robust equilibrium. And again, you could say, you could have A same modified definition with just requiring this property to hold for the impatient valuation in the neighborhood. It wouldn't change. It's the same result, a weaker result, but still true. But I do believe that this is the right conceptual concept to apply for other models of repeated games, like repeated games with incomplete information. There is the issue if it's a non-impatient valuation, there are some issues. So I think for the general, for extending this to other models of repeated games, I think taking this modified definition makes a sense. Now there was a question of Ehud, is there an issue about strategies? So I think one of the problems probably that most game theorists distance themselves from analyzing continuous time games, in particular continuous time stochastic game, because our approach is always, let's try to define from the extensive form description of the game a normal form. Let's define all strategies of this game and let's prove there the concept, apply there the concept of equilibrium. One of the first games I encountered before I knew what is game theory was the game of Man and Lion. Man and Lion. You're not familiar? Those who are not familiar. So it's a game in continuous time. It's a continuous time game for the audience here. You could prove what is the value. You could prove the optimal strategy of a player. You don't have to know all the strategies. You don't have to define that for any pair of strategies there is an history. Similarly here, I claimed usually when we say an equilibrium is a profile of strategies such that nobody can by a unilateral deviation benefit. Okay? So if I'll give you a profile of strategies, which this property, I don't have to define you the entire normal form game. So it's like we have an incomplete game. We have a list of strategy for player 1, a list of strategy for player 2, and we have a pair of strategies such that for every deviation of each one of the players themselves, the payoff is well defined. So for the concept of an equilibrium, I am done. And this was the way. Only you need the row and the column. You have to know that there it's well defined. So if you define properly, kosherly, what is an equilibrium, you can forget about all the rest of the game being well defined. You don't have to know what are the other strategies. And so this is here. I think sometimes there are trivial.
You have to know the strategies. You don't have to know the payoffs. The payoff against
you have to know the payoff also for these strategies.
You have to know what the strategies are.
Yes.
How do you define a strategy?
So there will be some well-defined kosher. If I tell you play always left, it's a kosher strategy, even if it's continuous time. Okay? I'll tell you pay left in time from 0 up to 5 and thereafter play right. There are many families of strategies that have a simple description and they are well defined. Okay? Now, if I'll give you a profile of such well-defined strategies, such that if it was a one-player decision maker, and he has to decide, let's say in a classical repeated game, his strategy from time 0 to infinity, he just has to define the function of his action as a function of time. Okay? So this will be a one-person strategy. Yes?
You have to define all the deviations.
Yes, but only against the strategy.
Only against this strategy. So if all the players are playing, so the basic concept there is to consider what's called discretamized strategy. If all the players are playing with a predetermined strategy between time 0 and 1, me, as a reacting player, I don't have to see what they are doing. If I deviate, I just have to say what I'm doing between time 0 and 1. So indeed, the constructions of the equilibrium strategies is such that it is being constructed with such strategy. Now, there is obviously also, I was a little worried at the beginning, okay, the game is not well defined and so on, and one could view also the continuous time as a kind of a limit of stochastic game with short stage duration. So a supplementary result to that is to try to look on the stochastic game which is constructed and say every 10 seconds I could change my strategies and modify the payoffs, and I get a game which I call short stage duration game. And you get that in these short duration games, there is an equilibrium strategy. Moreover, you could look on the equilibrium strategies that are listed here on this auxiliary continuous time game, and there is a natural map of them to all this short duration, because it tells you what to do between this time and that time, playing such an action, and you get that this is an equilibrium. 1 minute, okay? And so I won't cover the last topic that I wanted to cover. This, for those that will be interested, there are few open problems in the last topic that I mentioned, but I'll say one thing. Sometimes there is, when you prove something and you get something, there is sometimes a trivial observation that suddenly you don't realize that this was there. And what made the continuous time model working while the discrete time we are still all struggling, and after such a long struggle we probably think there is no uniform equilibrium or no equilibrium for that. And the basic point is that in continuous time you can apply reciprocity much more easily than in the discrete time. In a stochastic game, if it's a discrete time and at day one I say I'll do that and then you will do that. If he bluffs on you and makes something, you may with probability 1 or with positive probability fall into a trap that you could never recover. But if it is continuous time, the probability that he's trapping, so if he tries to trap me and I observe what his directions he's taking, I could immediately say, oh, he's not trusty, I cannot work with reciprocity. But he could play this action now, maybe a risk with very small probability that we fall into a good state for me and a very bad for him, and thereafter I'll compensate him. So reciprocity in continuous time is much more easy than in the discrete time, and this basically is what is pushing this result here. So you read it quickly, so I understand that you see that. So thank you. Any question? Yes?
So I strongly support the continuous time models, but if you have more than 2 players, say 3 players, then it seems to me that this thing that you only need to define it doesn't.
This was just to illustrate it for 2. If you have 3, I wanted that a pair of strategies, so it's now in the 3 space envision, but any unilateral deviation has 1 dimension, right? So I need then that the payoff, the play, everything will be well defined for any unilateral deviation. So I have, from a given point for 3 players, I have 3 different directions. And n players, it's n. Sorry?
But it's dynamic, then a deviation of somebody else may cause a deviation of the 3rd player. And
Sure. But the strategies themselves will be such, the actual equilibrium strategies that are being constructed here are such that they will say that I switch my time only at the time 0, 1/4, 1/2, and so on. So you change, only at the new time I'll start to reacting, but then everybody knows what I'll do in the next quarter of an hour, or in the next quarter of a minute. So the strategies themselves have to react to deviations, but they react in such a way that each time there is some horizon by which the play is well defined.
We have many questions, I see, and we are eating into our break time, so let's take 2 more. And that's it.
Yes, Jerome. Sorry?
You just talked about existence. In some case, what can you say about characterizing all the equilibrium?
So characterize, the characterization is definitely very important, as we know in the folk theorem. I don't have a general characterization. I could have a characterization in the case of absorbing games, and therefore, for all those that know, if you have for absorbing games, you have for irreversible games with only finitely many state changes. For this, you could characterize. For the general one, I don't know.
Like soccer, right? Soccer is irreversible. Because you're interested in soccer, no.
Yes?
You can follow referee TV.
Okay, thank you very much.